Welcome to the UGC lecture series. This is the EPG Pathshala lecture series on computer science and we are talking about the paper machine learning. So, in this module we will be talking about hidden Markov model. We have looked at the basics of hidden Markov model in the last module. Today we are going to look at some interesting aspects of how hidden Markov model has to be modeled. Okay. So, that is what we are going to look in this particular module. So, these are the people responsible for the development of this particular module. And now let us look at the learning objectives associated with this module. The first learning objective is to understand the three issues of HMM modeling, hidden Markov modeling. There are three problems as it is called, or questions or issues or whatever it is associated with HMM. Then we are going to explain for one of those issues how the Baum Welsh algorithm is used. Okay. And then we are going to look at the second issue here, which is decoding, for which we are going to discuss the Viterbi algorithm. The third issue will be discussed in the next module, not in this module. So, the key words associated with this particular module are forward probability, backward probability and the Trellis diagram. Let us do a small recap of the hidden Markov model. A hidden Markov model is an extension of the Markov model in which the inputs symbols are not the same as the states. In the Markov model, the input symbols and the states are the same. So, what you see is what you get, but in the hidden Markov model, we do not know which state we are in, that is the state is hidden, only the observation is given. So, we are going one more level of abstraction. For example, a typical example of explaining HMM was pause tagging or the part of speech tagging, where the input symbols are the words and the states are the part of speech tags. So, we see only the part of speech tags. So, the Markov assumption that we will be doing is the state transition that we do from one to the other transition is dependent upon only the origin and the destination, not on other things. There is another output independent assumption. All observation frames are dependent on the state that generated them, not on the other observation frames. So, we are only bothered about the observation is based on the state. It is not based on what was previously observed or neighboring states gave. So, these are some assumptions we make if we have to model this any problem using hidden Markov model. So, in this particular module, we are more bothered about how we decide on the parameters of HMM. We will come to that. So, first let us discuss some of these parameters. One is states. So, the hidden Markov model will be associated with a set of states S, which will be S1, S2 to Sn, which will be the number of states. Then comes the transition probability. The transition probability will give me normally represented as A11, A12 to An, where Aij represents the probability of making a transition. What is the probability of going from one state Si or making a transition from a state Si to a state Sj. So, that is called as transition probability. Next we have what is called emission probability, which is a set B of functions of the form BIOT, which is the probability of observation. What is the probability of observing the OT at a particular time, the T is associated with the time of observing T when we are in the state Si. So, what is the probability of observing O at T given that we are in the state Si. So, that is called the emission probability. And then we have an initial state probability called pi of I, that is the probability that one of the states, remember we have S1 to Sn states, what is the probability of each of this state being an initial state. So, that is called the initial state distribution. And M is the number of distinct observation symbol per state. So, each state can be associated. For example, if you take pause tag, this particular noun can be associated with so many distinct observations, that is the M. Normally, M does not come too much into our picture. So, the two model parameters that we talk about are N and M. N is the number of states and M is the number of distinct observation symbols associated per state. And there are three probability measures: A, the transition probability; B, the emission probability, the emission of a observation symbol from the state Si give at a time t, and then you have a initial state distribution, which is the probability that a state Si can be the initial state. So, these are the three probability measures. These are the parameters of an HMM. So, just to recap, you have S, K, pi AB. Pi AB are the S1 to Sn are the values of the hidden states, V1 to Vm are the values of the observation or k or whatever, and then yes, pi a b are the 3 probabilities. Okay. So, we are more bothered about the probabilities. Pi are the initial state probabilities, aij are the state transition probabilities, and bik are the observation state probabilities or the emission probabilities as it is called. Now, these are the 3 problems or issues that is normally associated with HMM. The problem 1 is evaluation. You compute the probability of a given observation sequence. So, you are given an observation sequence, compute the probability that observation sequence will come given the model. The second problem is decoding. We will go a little more in detail as we go along. Given an observation sequence, compute the most likely hidden state sequence. Now, please note what is the meaning of this in terms of pause tagging. Remember, part of speech tagging is you have words and you have the part of speech tags. Now, the words were the observation, the part of speech tags are the states. So, compute the probability of a given observation sequence means the man eats the carrot. So, what is the probability that that particular sentence will come? And given that sentence, the man eats the carrot, what is the probability that the determiner man is noun, eats is verb, the is determiner, carrot is noun. So, what is the probability that this is the most likely hidden state sequence? I have told the correct one, but we have to find that out. So, that is the decoding problem. So, the tagging problem, okay, is actually the decoding problem. And you have a third problem also, which is called learning. Given the observation sequence and a set of possible models, which of the models fits the data, which means you have to find the model parameters. Okay. So, that is the hardest problem to solve. That we will not be discussing in this module, we will be discussing in the next module. So, in this module we will be discussing evaluation and decoding. Okay. Now, before we go into that, let us see how an observation sequence can be built. Given the above 5 elements, we can build the observation sequence. O is equal to O1, O2 to OT, where T is the number of observations. This observation sequence is built as following. You set the time T is equal to 1, choose an initial state Q.I. is equal to Si according to the initial probability distribution. Then choose OT is equal to Vk according to the symbol probability distribution. Okay. According to the symbol probability means what is the probability at that state Si, this particular symbol comes. Then you have to transit to a new state according Sj according to the state transition probability, and then you set T is equal to T plus 1 and then go back and find out which is the next observation according to the symbol probability distribution, and then you keep going which is the next state and so on till T is less than or equal to capital T, which is the number of observations. So, this is basically building an observation sequence. So, here we assume we know everything, so we can build the sequence. We have discussed this a little bit with a small urn example in the previous module. Now, so as we again said, these are the 3 discussions or the 3 issues, problems, questions. So, the first problem is evaluation. So, we are given the observation sequence O1, O2 to OT, and we are given the model. What is the meaning of we have given the model lambda? That means we are given all the probabilities required. We are given the initial probability of each and every state, we are given the transition probability from one state to the other, we are given the emission probability also. So, if we reach up this cell, what is the what will be emitted? So, we want to compute the probability of the sequence given the model. So, that is the problem. So, the probability of the sequence is what we want, and this is done by the forward backward dynamic programming algorithm, which is called the Baum Welsh algorithm. So, we will be discussing this algorithm. The second problem is decoding. So, given the observation sequence O is equal to O1 to OT and the HMM model lambda equal to A, B, pi. Remember, A is the transition, B is the emission and pi is the initial probability. How do we find the state sequence that best explains observation? Previously, we said that what is the probability of that sequence. Here we are saying that we want to find the best state sequence that gives me these observations. Okay. So, again, what is the probability of that set of words coming is what we do during evaluation. What is the probability of these given that observation, what is the probability maximum, which state sequence will give me the best probability is what we are trying to find out here. So, compute the most probable sequence of states given the sequence of observation and the model, and this is done by what is called the Viterbi's dynamic programming algorithm. And the third problem, which we are going to discuss in the next module, is how do we adjust the model parameters. What are the model parameters? The model parameters are the transition probability, the emission probability and the initial probability, such that given the model, the probability of observing that sequence is the maximum. So, learn the best model given the observation. This is done by what is called the expectation maximization heuristic, the EM heuristic. So, these are the three major algorithms: Baum-Welsh algorithm, the Viterbi algorithm and the expectation maximization heuristic. So, for evaluation, that is finding the probability of the observation sequence is done using the Baum-Welsh. Finding out the best probable sequence of states given the observation and the model is done using decoding using Viterbi, and then given the data, given the observation, we adjust the parameters such that you get the best model. That is done using the expectation maximization heuristic. We have looked at the fundamentals of expectation maximization previously. Here we are going to look at how it is used in hidden Markov model, but not in this module. We are going to talk about this in the next module. Now, before we go along, we said that HMM has the assumption of the Markov assumption. The Markov assumption states that the probability of the occurrence of the observation is a word Wi at time t depends only on the occurrence of the Wi minus 1 at t minus 1 and not on other things. So, the probability chain rule of the observations or the words W1 to Wn is I is equal to 2 to n. Probability of Wi is dependent on probability of W1 to Wi minus 1, but that is reduced through the Markov assumption as approximated to P of Wi is dependent not upon all the previous states, but only on the just previous states Wi minus 1. So, this is the Markov assumption. Now, normally this hidden Markov model is represented using a trellis. This is the trellis diagram. So, you have an initial state S0 and you from S0 you can go to S11, S12, S13, S14. This is just to tell you that it is at state 1, 2, 3, 4 at time 1. Then from S11 you can go to S22, you can go to any of the other 4, that is at time observation time T2 and so on, and finally you land up at 0t at ST1, ST2 and so on. So, this is just to tell you that you have a state associated with each of the observation points, time it could be. So, O1, O2 to OT. So, this is the trellis, and we will talk now about the forward backward algorithm. So, the likelihood is measured using any sequence of states of length t. This is known as any path method. So, here what we are doing is, this is to tell you the difference between Baum-Welsh and the Viterbi algorithm, but at present what we are trying to say is, we are just trying to find out the observation sequence and the probability of the observation sequence, whatever may be the path used. So, it is called a any path method. The second option is we choose the PMM by the probability generated using the best sequence of states. So, there we are not bothered about any method, we have to at each and every point we are going to choose the best possible. So, this method is called the best path method. Actually, any path method is the Baum-Welsh and the best method is the Viterbi, that is used for decoding and this is used for that is used for evaluation and this is used for decoding. Now, let us discuss what is the meaning of this forward probability. Now, what is the probability that given an HMM model lambda at time t, the state is Si and the partial observation 0,1 to 0t has been generated. So, what is saying, imagine the trial is you are given the model lambda and now you have a time t and a state I. What is the probability of generating the partial observation 0,1 to 0t? Up to that you have come from 0,1, you have reached 0t and you are in state I, what is the probability? So, that particular probability is called the forward probability. Why is it called the forward probability? You are going from 1 up to t. So, lambda t of I, the probability of being in state I at time t is equal to the probability that you have seen the observation 0,1 to 0t and the current state is Si given the model lambda. So, this is called the forward probability. So, let us understand the forward probability using the trellis. So, the probability is as we have defined there, the lambda t of I, that is the forward probability of the state I given at a time t. Okay. So, t is what we want to find out. We should have t minus 1 if you have to find out t. So, alpha t of j, okay, that is you are going from I to j, the probability of going from I to j is alpha t minus 1 of I aij bj 0t. I will explain what this means. The probability of being in state j at time t is nothing but the forward probability of having reached t minus 1 with state I, and there being a transition probability aij, that is transition probability of from I to j, and the probability that the emission probability at the jth state is 0t. I will repeat this. You have at t minus 1, you have alpha of t minus 1 is 1, alpha of t minus 1 is 2, alpha t minus n is whatever. So, now what we are trying to do is from 1 you go to j, from 2 you go to j, from n you go to j. So, that is why we have 1 to n. Now, we want to find out what is the forward probability that at time t you will be in the state j, given that at the you are going to take a summation of all those probabilities and you are going to sum it. So, that what are we doing by summing, what probability are we summing? We are summing the probability of having reached at t minus 1, having reached each of these states, and the transition probability, that what is the transition probability of ai, a1j, a2j. So, this 1, 2 to n is the states that we are associating at t minus 1. So, you have at t minus 1 you are at 1, then you take a transition 1 to j and you have landed at b, and then you are also given that the observation at that particular point in t is OT. So, we are also looking at what at each state having an emission probability of B of j. So, this is the forward probability. So, you can see that you are doing a summation operation of all the forward probabilities that you have seen up to t minus 1, and then taking a summation of that along with summation of each of the states along with its transition probability and the final emission probability. So, now determine the probability that a particular sequence of symbols O was generated by that model. So, what you are going to do is, given that the particular sequence Q is generated by the model M, given the model M, this is a sequence. The first one is, so let us assume the sequence is Q1 to Q.t. So, initially first you will start with the initial probability Q1, then from t is equal to 1 to t minus 1, you will look at the A Qt to Qt plus 1 is equal to pi Q1 into A of, that is the transition probability from Q1 to Q2, Q2 to Q and so on up to Qt minus 1 to Qt. Similarly, the probability that given that sequence, okay, that sequence and the model, this is the transition sequence. So, you are given the transition sequence, given that transition sequence and the model, we are now looking at the probability of the observation. So, t is equal to 1 to t, probability of seeing the observation given Qt comma m, which is nothing but the emission probability of Q1 giving observation 1, Q2 giving 2, Q2 giving OT. So, finally, given the what is the probability of the, see Q is the state, O is the observation, okay. Q is always one state to another is determined by the transition probability. Given a state, the observation coming out is given, that is the way of understanding it, emission probability. And then what is the probability of the output sequence given the model is given by the two combined together, probability of the observation given Q, that is the state sequence and the model, and the probability of the state sequence given the model. So, this is how we define evaluation. So, this is a forward recursion problem, as you would have understood. You calculate the forward probability, one set of probability, go to the next using this, go to the next using this. So, that is the forward probability. So, this we have already discussed. So, alpha, what is the probability of being in state I at time t is nothing but the probability of observing 0 1 to 0 t being in state I given the model. So, initialization is alpha 1 of I, that is the probability of seeing the first observation at at time t1 at the state I. What is the probability, forward probability? That is nothing but the initial probability of the state I and the probability of observing or emitting the observation O1 at the state I. So, that is the initial that can be given without calculating anything else, everything is given to us. The model gives you that pi and b, so nothing is needed. Now, for alpha t plus 1 of j, this is what we said, you have to take the summation of all the previous states and their transition probability, that is the first part of the summation, into you have reached j. So, you are in the previous t minus 1, you are in the ith, you are in all the state I, that is what is that I summation is giving you, and then you have reached the state j. Now, in the state j, what is the probability of emitting 0 t plus 1, okay, given jth state. So, at the state jth, what is the probability? That is your emission probability. And the termination condition is you have reached, you have seen all the probability, you have seen the complete sequence and you are at I, and the model is given. So, it is nothing but I is equal to 1 to n alpha t of I. So, this is the forward recursion problem. So, you are starting with 0 or 1 and reaching the tth. Now, let us understand the hidden Markov model using a small numerical example. It is a trivial example, it is taken from this particular small PDF. So, you are trying to find out the probability of the observation sequence R red, red, green, blue given the model. Okay. Now, the model has been defined for you. How have they defined the model? They have told you that the initial probability of you have 3 states S1, S2, S3, and the probability of being in S1 is 1, the probability of being in S2 is 0, and the probability of being in S3 is 0. And you are also given the transition probability 1 to 2, you can see there. For example, 1 to 1 is 0.5, 1 to 2 is 0.4 and 1 to 3 is 0.1, like that it is given. Now, and you are also given the RGB there. So, that you understood what is the initial probability, you are given the transition probability, and on the side of that as a row matrix you have been given the probability of emission. So, being in 1, what is the probability of emitting red is 0.6, green is 0.2, blue is 0.2. In state 2 it is 0.2, 0.5, 0.3 for red, green and blue. Similarly, at the third state it is 0.0, 0.3 and 0.7. So, this is the emission probability. So, the 3 things is the model, the initial probability, the transition probability and the emission probability. Now, let us take the problem. So, 1, now you can only be in state 1 as initial probability, because that is what the others give 0, but just to completeness sake 1, now what have you observed R? So, you have to take only the from the emission you have to take only what the probability of that particular state emitting red. So, 1 initial probability into the probability of emitting red in that state. So, 1 into 0.6. Similarly, from the second column matrix, the second state probability of emitting is 0.2, but the probability of being in the initial is 0, probability is 0 and this is also 0. So, that is about 1. Now, this is the interesting part. Now, from the first state, okay, what is the probability of going to you have got a state, first state, and you have got an R, that is you have got red. Okay. So, from 1 to 1 the probability is 0.5 and the probability of emitting R is 0.6. Okay. From 1 to 2 the probability is 0.4 and the probability of emitting red is 0.2. From 1 to 3 the probability is 0.1 and the probability of emitting red is 0. So, with that you calculate. Similarly, for the first state, second state, probability you cannot go to 1. From 2 to 2 it is 0.6, probability of red is 0.2, that remains the same. And then from 2 to 3 it is 0.4 and the probability of emitting is 0. So, you have those values. Okay. Now, please note that for example, in the first one there is no summation, but in the second and third, okay, 0.048 value is a summation of the 2 values that you have got, that is from 1 to 2 and 2 to 2. And similarly, the third one, though it is 0, is 1 to 3 and 2 to 3. Like that you take a summation, find out that into the probability. So, that is how you get, and similarly you go on, and finally you see you have probabilities 0, 0, 1, 8, 0, 1, 1, 2, 3 and 0, 1, 5, 3, 7. That is the probability of generating RRGB given the model. So, and the transition that happened. Okay. So, in the naive approach, the forward algorithm takes on somewhere about the order of n square t computations. The backward probability is analogous to the forward probability, just it is in the other direction. What is the probability that given a HMM model lambda and the given state t is I, the partial observation t plus 1 to t is generated. It is not given 0 to 1 what is generated. So, beta of t in the ith state is the probability of generating 0 t plus 1 to t. Remember previously we were doing 0 1 to t in observation 1 to observation t. Here we are saying 0 of t plus 1 to t given that you are in state I Si and you are given lambda. So, we are not going to go too much into the details, but it is similar to the previous algorithm, but you are going from the backward state, that is all. Okay. So, this is the algorithm, and the initialization here is you do not have beta t of I is equal to 1 because you are starting from there, and the induction is similar to what you would do, but it is in the backward direction. You will find t. For finding t you have to take t plus 1. Remember previously we used to find t by taking t minus 1. Here you have to find t, that is you are taking all the states from t minus 1 and to find t. Here to find t you are taking all the states from t plus 1. So, the termination condition is give what is the probability of the observation given sequence given the model is given by this. The second problem is decoding. Now, decoding is given the observation sequence the same that we were given previously and the HMM model. Now, we do not want to find the probability of the observation sequence, we want to find the probability of the state sequence, the hidden state sequence. So, what we want to find is the most probable state sequence. For that we use the Viterbi's dynamic programming algorithm, and the solution to problem 1 evaluation gives us the sum of all the paths through the HMM efficiently. For the second problem, which is the decoding, we want to find the path with the largest probability. We do not want all the, we were given everything, we do not want that. So, given a set of symbols O, determine the most likely sequence of hidden states Q that led to these observations. So, we want to find the sequence Q is equal to Q1 to Q.t, which maximizes the probability of the Q, that is given the set of observations, what is the most maximum sequence that gave me this observations. So, in other words, we want to find Q dash such that is Q dash is a sequence of states. It could be a number of sequence of states. We want to find that particular sequence which maximizes my probability given the observation sequence of observations and the model. So, the most probable state sequence is what is this question 2 or problem 2. If we know the identity of Qi, then the most probable sequence on I plus 1 to n does not depend on the observation before Ti, that is of course the idea. So, the Viterbi algorithm is an analysis of internal processing result, and the best most likely state sequence is what is given. So, this is a dynamic programming technique. This is similar to the Baum Welsh, except that here we are considering the the state sequence that gives me the maximum. So, the Viterbi algorithm similar to computing forward probabilities, but instead of summing up our transition from the incoming state, we did a summation. Here what we do? We will compute the maximum. So, you can see the difference there. That was the forward there where we did a summation of the previous states. Here what we do? We do not do a summation, we select the state that gave me the maximum. Okay. So, the maximum I that gave me that transition alone I am considering, that is the major difference between the two. So, in that decoding you have the forward procedure, you have the reverse backward procedure, and then you do a combination of the two. So, the Viterbi algorithm initialization is very similar to what we did for Baum Welsh. Induction, except for the you find the maximum probability state sequence from. So, suppose I am going to this state, which is the state that gave me the maximum, only that I will consider, I will not take the summation, that is the major difference. And so, I have that, I do that for each and every state. So, now I will get a particular state sequence only, I will not get all the states. So, the termination is of course when I reach the teeth observation, and I will read out the path. So, I will have probably S1, Si, which is the next state, which is the next state at time t1, t2, t3. So, S1, S2, S1, S3, so on. So, that is the best sequence that I will find. So, probably that for each of those observations, which is the best state sequence. So, that is the Viterbi algorithm. As you can see, I will be going through one particular path only. I will, if the best path ending in Q.t equal to Sj goes through Q.t minus 1 Si, then it should coincide with best path ending at that. That is the basic general idea that we had. And so this is the maximum. So delta j of t is equal to maximum of x1 to xt minus 1, and that is x1 to xt minus 1, 0 to, I mean observation 1 to observation t minus 1, xt is equal to g, and this. The state sequence will maximizes this probability seeing the observation up to t minus 1, landing at state j, and seeing the observation at that state t is what we are talking about. So that is the maximum. This we have already spoken about. So this is an example, the previous example itself, but we choose the maximum. So out of these three, 0.6 was the maximum. The next is, so you go from S1, S1, S2, S3, whichever is the maximum. So it is similar to the previous, except that we do not take the summation, we take the maximum. I think this will explain it to you. So in this particular module, we have explained the three issues. We have discussed the Baum-Welsh algorithm for evaluation using given the model, and also how to find the best sequence which would give me the observation given the model, which was called decoding, for which we use the Viterbi algorithm. Thank you.